Hello there. Let's talk about one of my absolute favorite algorithms to discuss, the quicksort sorting algorithm. So basically, for this first set of lecture slides, we're just going to talk about how does quicksort work, and to talk about how quicksort works, we'll look at really what it's built upon, which is this idea of partitioning. And there is an exercise. There's nothing sort of hidden behind my face here. There is an exercise associated with our partitioning slides. If you want a fun video to watch, I highly recommend this video here. Let me know if you watch that on Slack. Alright, so why quicksort? It's a very simple algorithm. The running time is going to be on average. So a preview here, that's an average running time. Average is going to be big O of n log n, just like merge sort's average was big O of n log n. Merge sort's worst case and best case were also n log n. Those will be different for quicksort, as we'll see. Quicksort is superior to other n log n algorithms in a few respects. It has very small hidden constants because of this idea of in-place partitioning, which we'll talk about in the slides. And it's fun to talk about because this will be our first stochastic algorithm. So our first algorithm with any sort of randomness to the process. We won't be looking at randomness in this set of slides. We're just going to assume we're going to make a couple of assumptions that mean we don't have to worry about randomness. But for computing the running time, we'll start talking about randomness. And your next assignment will have a random implementation of quicksort involved. Alright, so what is quicksort? It's an algorithm that takes as input an array of n elements in any order, and it outputs a reordering in non-decreasing order. The key idea for quicksort is to partition the array around something called the pivot element. Alright, so what is the pivot? You just pick an element and you call it the pivot, and you rearrange all of the elements in the array so that everything to the left of the pivot is less than the pivot, and everything to the right of the pivot is greater than the pivot. And quicksort works perfectly well with ties, but let's just ignore them for now. It's not going to be something we'll worry about when we're computing the running time or when we're doing a proof. Alright, so you could call this a partial sorting into buckets, essentially. One bucket of the greater than, one bucket of the less than, and then a bucket with just the element. Well, after we've done this partitioning, what can you tell me specifically about the pivot element? Well, something interesting about the pivot element is it's now in its correct spot. So each time we call partition, we put at least one element in its correct spot, which means we've made progress towards our sorting goal. What would be the running time of calling partition on every element? Well, I've not given you the running time of partition, but you can kind of assume that we have to loop over all elements, which means it's linear. So it would be big O of n, linear operation that we're doing n times, once for each element, which would be a big O of n squared. So your tip here is we're not going to be calling partition on every single element. That's not very cost effective in terms of computing. Alright, so what is partitioning? What does it actually look like? Well, we have an array like this, and let's just say we have an output array, and we say, okay, well, here's our pivot. Is 8 greater than or less than? So it's greater than, we put it at the end of the array. 2 is less than, so we put it at the front. 5 is greater than, 1 is less than, 4 is greater, so are 7 and 6, and then finally we can put the pivot in its correct spot. At this point, we end up with just a picture that looks like this. We have a bucket over here, they're not in sorted order. We have a bucket over here, they're not in sorted order. So if you notice, the 2 and the 7 are not in the correct order. The 2 and the 1 and the 4 and the 7 are not in the correct order over here. But the pivot element is in its correct sorted spot. Alright, so here is your exercise for this set of slides. Pivot around hello. So normally we do numbers. I just want to remind you that when we're sorting, it doesn't always have to be numbers that we're sorting. So let's say we're sorting these strings here alphabetically. Okay, well, you don't have to have come up with exactly this, but as long as hello is in its correct spot, your buckets can really be anything. I'll just kind of work through this in the same way that we did before, which is A comes before H, Y comes after, HO comes after, T comes after, D comes before, C comes there, and so on. So if you ended up with something like R doing class, hello, and let's see, I'm losing my spot here. Today, how you. I think that's right. If not, I think you get the idea at least. That's what you should end up with after a partition around hello.